Okay, so I want to finish off today talking about optics. So this is really the province of Shabnam Qadir, who was kind enough to instruct me about what to say today. So let me report on some generalities and then report on Shabnam's results for the optics, which is work still in progress, but rather interesting. So the optic is the space, fairly obvious notation. You take a P4, but with weights 1, 1, 2, 2, 2, and an equation of degree 8. So by the 1, 1, 2, 2, 2, we mean that we take x1, x2, x3, x4, x5, and we identify with lambda x1, lambda x2, but lambda squared x3, lambda squared x4, lambda squared x5. Okay. Now, the fact that one does that automatically is not entirely trivial, these identifications, because suppose this is true for all lambda, so in particular if you take lambda equals -1, it's true, and so this identifies this space with minus x1, minus x2, x3, x4, x5, and so there's a Z2 action, and there's a fixed point set, so there's a fixed point set, which is 0, 0, x3, x4, x5. So this space you can think of as a quotient of a projective space, and the quotient is singular. And so, so the discussion of this space involves a discussion of the resolution of the singularities, and this leads, of course, rapidly into toric geometry as being the right language in which to discuss all these things. Okay, so I'll say some things about toric geometry as we go along. So that's the space. Why is it Calabi-Yau? Well, it's Calabi-Yau because, of course, you can construct a 3-form in the way that we did. The optic, well, this is an equation of degree 8, so if you like, we'll write one down if you want to look at one. So we could, for example, take P to be x1 to the 8th plus x2 to the 8th plus x3 to the 4 plus x4 to the 4 plus x5 to the 4 minus 2 phi x1 to the 4th, x2 to the 4th, minus 8 psi x1, x2, x3, x4, x5. Okay, so that's an equation of degree 8. Okay, of course you count the degree according to the scaling rule. So this gives us a manifold M. Okay. This optic has, of course, been chosen with a certain benefit of hindsight, and the reason is that this is invariant under a group G, so there's a group G, which you can describe in several ways. One way to describe it is that you take x1, x2, x3, x4, x5, and you map that to alpha to the n1 x1 ... alpha to the n5 x5, where alpha to the 8th is 1, so alpha is an 8th root of unity, and this quantity A, so let me define A and then set it equal to 0, so A, which is n1 plus n2 plus 2 n3 plus 2 n4 plus 2 n5, if A right? So what we do is we choose the group of all such transformations such that A is congruent to 0 mod 8. Okay, so that gives us a group. In fact, group G as an abstract group is Z4 cubed. Okay. Now there are two ways, and the importance of this group is that if we take M and quotient it by G and resolve, then we get the mirror manifold. Okay. And again, this polynomial is the most general polynomial invariant under these transformations. Okay. So that's our octic. It has, I'll explain how we calculate this in a minute, but this one is interesting because H1 of M, so let me go on to another sheet. H11 of M, it turns out, is 2 this time, and H21 of M is 86, and 86 is 83 plus 3, and I'll come back and discuss what I mean by 83 plus 3 in just a second. Okay, so this one's interesting because the mirror is going to have two parameters, right? So this one has two Kähler structures. The mirror will have two parameters. Okay. Another way, we defined a second ago this quantity A, and we defined this transformation, and we could have done things a little differently, which in some ways is better. So let me put that up on there. We can see that. What we could have done is include psi and include the parameters in the transformation. So we could have written x1 to x5 and then psi and phi, and we could have sent that to alpha to the n1 x1 dot 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 alpha to the n5 x5, and then send psi to whatever we have to send it, psi alpha to the minus a and phi alpha to the minus 4a. Is that true? Yes. Yes. You see that if you do that, then the equation's invariant without having to restrict alpha to be 0 mod 8, without having to restrict a to be 0 mod 8. So if you like, this is a nicer way of forcing the equation to be symmetric. You just correct the parameters. But this tells you that psi, under this change of, you regard this, if you like, as a change of coordinates, under this change of coordinates, psi and phi are not invariant, and they change by, well, you see that psi changes by 8th roots of unity, and phi changes by square roots of unity. So the natural coordinates are psi to the 8th, psi to the 4th phi, and phi squared. Those are the coordinates which are invariant under these transformations. Of course, only two are linear. Only two of these are independent. Okay. So let me describe this. Let me now say something about toric geometry. So the first of these is, how does one calculate these numbers? Well, there are wonderful formulae due to Victor that tell us how to calculate these formulae. And so we have, the basic idea is that there are a pair, as we discussed yesterday, a pair of polyhedra. There's delta, the polyhedron, which is the Newton polyhedron, and nabla, which is the polyhedron over the fan of the toric variety. And these Hodge numbers can be computed from the combinatoric data of the polyhedron. So H21, for example, is H is the number of points of delta, so the number of lattice points, minus you subtract off, you look at the codimension 1 faces of delta, and you subtract off the number of points in the interior of the codimension 1 faces in that way. And you haven't quite finished, you add in, there's a contribution from codimension 2, and here you write int theta star, and then you subtract 5. So int theta star means that in theta, so you have a theta in delta, phase theta in delta of codimension 2, and this corresponds to an edge. An edge, theta will have dimension, the 4-dimensional polyhedron, these faces have dimension 3, these faces have dimension 2. Theta's codimension of a 2-face of delta corresponds to an edge of the dual polyhedron. So what you're supposed to do is make this pairing between faces theta in delta and theta star in nabla, and you multiply it by a correction term which involves the number of interior points in theta multiplied by the number of interior points in the corresponding dual face, and then you subtract 5. Okay, and H11 is the obvious dual statement, points of nabla minus sigma int theta, if you like, in theta star, code in theta star is 1, theta star in nabla, plus sum here int theta star int theta minus 5. Okay, so it's very beautiful relations which give you the Hodge numbers in the
Is that H12, or why is it not?
well, H12 is H21, so there's nothing to be gained. Okay, so one gives us the number of complex structures and one gives us the Kähler class. And of course it's manifestly mirror symmetric, because if you interchange delta with nabla, you interchange the two numbers. Okay, now these formulae are very useful in practice. So in practice this is how you calculate the Hodge numbers. But also this is this 80, if you do this calculation for this manifold, these two terms between them give you 83, and this term here gives you 3. Okay, and what this means is that there are 86. As a complex manifold, it has a certain Hodge number, and that Hodge number tells you the number of ways you can deform the complex structure, and that number of ways is 86. Okay.
How do you cancel your delta from your equation?
You take all the monomials and you make the Newton polyhedron of the monomials.
But you have a homogeneous one. You have 5 variables.
This will be...
You have to be homogenized in some way. Or...
7 variables. The polygon is just a section of this 5-dimensional.
Right, but they will all lie in a plane.
So you start with the 5-dimensional particle, and then you take...
So the monomials, they are lying in 4-dimensional space. Because of the condition.
We had this on a picture yesterday. Well, the question is whether we can find yesterday's.
What if you put an origin?
No, okay, let me draw a picture. All things are easy. Okay. If we did this, right, there's nothing special about this case we're dealing with. If we do this for a cubic, xi cubed minus 3 phi x1, x2, x3, is 0 as we did yesterday, then you plot the monomials in a three-dimensional space and they give you a polyhedron like this. So this is something that we've already seen. And so, although it's a three-dimensional figure, the polyhedron you get is a two-dimensional plane inside the three-dimensional space. And then if you refer it to an intrinsic basis, then it gives you this figure. So, like that. So although it looks as when we start with the octic, it looks as if there'll be a five-dimensional polyhedron. It is in fact a four-dimensional polyhedron. Right. Well, no. Consider the cubic, right? So the monomials are 3, 0, 0, 0, 3, 0 in an obvious notation, so on, and then this one is 1, 1, 1. So it looks as if the figure is going to be three-dimensional. But it's not three-dimensional because when you draw it, all the points lie in a plane. They all lie in a plane because sum of the exponents is 3. Right. So what we do is, so the polyhedron that you get is in fact two-dimensional. Right. And so if you refer the diagram to an intrinsic basis like this, then it looks like this. Okay. In the same way, the other polyhedron is four-dimensional. So we were discussing this 83 plus 3 split. This is interesting. So as a complex manifold, as a complex manifold, H to 1 is 86, and that means you can deform the manifold in 86 independent ways. However, you can't deform it in 86 independent ways while it's embedded in this weighted projective space. You can in fact only deform it in 83 ways. So if you ask how many ways can you play with the coefficients in the polynomial, you'll find that there are in fact only 83 ways that you can do that. And there are 3 extra deformations. That's what's counted by the second term here. There are 3 extra deformations which the manifold has, which you cannot realize while keeping it embedded in this weighted space P4 1 1 1 2 2 2. Okay. So that distinction comes up a little later. Okay. Then there's a discussion of the periods and the Mori cone. Okay. So one could write more generally P is C1 y1 to the 8th plus C2 y2 to the 8th plus C3 y3 to the 4 plus some terms, right, obvious terms, plus C6 y1 to the 4th y2 to the 4th plus C7 y1 y2 y3 y4 y5, and one could apply the sort of the general toric procedure that we talked about yesterday, and we would have divisors corresponding to the vanishing of the coordinates. So you write down this matrix 1 1, there's 6 of these, 1 1 1 1 1 1, and then 1 8 0 0 0 0 1 0 8 0 0 0. I'm writing down the powers here of the various coordinates. 1 0 0 4. This is not entirely trivial. It is different from the quintic 1, 0, 0, 0, 4, 0. And then we have one too many columns. 1, 2, 3, 4, 5, 6. No, we're doing well. Right, you prepend a 1. That's part of the rule. Okay, D5, 0, 1, 0, 0, 0, 0, 4 is good. Okay, this term is in this first row. I've now written down all of them except this one, and this one now we have to write down as 1, 0, 0. No, 1, 4, 4, 0, 0. 0. Okay, and then the columns of this give us relations. So these are divisors: D0, D1, D2, D3, D4, D5, D6. And we get various relations between them. The first column tells us that D0 is minus D1 plus dot 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 plus D6. Then we get the next, the last three. It's good to do the last three next. So if we look at this column, it tells us that D0 is minus 4D3, and if we look at this column, it says that D0 is minus 4D4, and the last and this column, yeah, that's right.
D3 plus D6. D0 is minus 4D3.
I'm looking at this column.
Yeah, but there's a 4 at the... Oh.
No. You're displaced, but we're displaced by 1 relative to each other. Right, and then there's minus 4d5, and again, so there are other equations that say that, for example, if we look here, that d0 is minus 8d1, it must be minus 4d6, and d0 is minus 8d2 minus 4d6. Okay, so you get a system of equations like that, and this tells us, for example, that D3 is D4 is D5, so give it a name, we call that H, and D1, you can see from these two equations that D1 and D2 are equal, so D1 is D2, and give that a name, so we call that L, and then you solve the equations, you find that D6 is H minus 2L. Okay, and these are, so we've written all the divisors in terms of two divisors, H and L, corresponding to the fact that H11 was 2. Okay, and then one can further study the intersection ring of these divisors, and one discovers that H cubed is 8, H squared L is 4, and HL squared is L cubed is 0. So those give you the intersection ring of the divisors. Now all this, well, not this as such, this is somewhat improved on what was done, but the background to all this is in this reference that I gave, in the third reference on the Octic paper written some years ago with Katz, Morrison, Ana Maria Font, Xenia de la Osa, and myself. Okay. So that paper gives a lot of the background on the geometry of these manifolds, and some of this has been streamlined since by application of these toric techniques. Okay. There's a procedure for finding the generators of the Morricone. Oh, okay. So I've said something slightly loud. No, we can find the generators of the Morricone, One follows a standard procedure to find the generators of the Mori cone, which I won't explain. It's somewhat long. And one finds -4, 0, 0, 1, 1, 1, 1, and the other one, so I think we should call this H, is that, and L is 0, 1, 1, 0, 0, -2. So all this follows the notation that we established in the discussion of the quintic yesterday. And this gives a basis dual to the Kähler cone, and our basis is chosen such that h dot h is 1, h dot l is 0, of course, L dot h is 0, and L dot L is 1. Okay. In terms of all this, one can write out the periods. Well, one could do two things. One is one could write down the natural variables. Okay. So there are natural variables, so we can call them lambda. Lambda is c to the h is somewhere. Okay, a c to the h, which gives us C3, C4, C5, C6, right? That's these four ones times C0 to the 4. And if you look at what that means in terms of psi and phi, this is minus 2 phi over 8 psi to the power 4. And another variable, mu, which is C to the L, which is, as you can see, C1, C2 over C6 squared is 1 over 2 phi squared. So these will be the variables in which it is best to express the periods and in which the number theory will be most apparent. Now, I've gone through this. This is partly a historical thing. When we did this work years ago, we didn't know as much toric geometry. At least I didn't know as much toric geometry as I do now. And the work was in fact held up for quite a long time just by questions of finding the right variables. I mean, it seems a trivial matter. You have two parameters. But there was the question of discussing the mirror symmetry and finding the right points in the moduli space where the quantum corrections would go to 0, and in fact that was held up for quite a long time by not being able to decide what the correct variables are, and this procedure gives the correct variables. It also gives the correct variables in which to study the periods from the point of view of arithmetic. Okay, so here it is a formula from yesterday, which you can now substitute into to find the Frobenius period. Here, gamma, which runs over the Mori cone, will be NH plus ML, and the rest is all straightforward. So this will give us a double expansion in terms here of this will give us a double expansion. These will be gamma functions, which will involve H, which will involve H, which will involve